Okay, so what I want to tell you about in this talk is I want to tell you some things about the relation between Higgs bundles on a Riemann surface and geometric structures, either on the surface itself or on some spaces associated with the surface. So the starting point for this is the non-abelian Hodge correspondence, which has come up many times in the last 2 weeks. So this is a relation between two different moduli spaces. So for us, the setting is going to be, we have a closed-oriented surface, which if you give it a complex structure becomes a Riemann surface. This will have genus bigger than or equal to 2. And then we have two moduli spaces. One of them is the space of representations of the fundamental group of this surface into a Lie group G. And for us, G is going to be a real Lie group, but we're not going to be talking about real Lie groups in full generality. We're going to be talking about real forms of a complex, of a simple complex group, and we're going to restrict to subgroups of SLNC for the purpose of this talk. And then the other moduli space is the moduli space of G Higgs bundles on the surface, and we'll unwrap as we go along exactly what that means. So the non-abelian Hodge correspondence says that these two spaces obtained in very different ways are homeomorphic. So when I want to talk about either one of them or both of them, I'll just use chi of G to represent either one. Okay, so whenever you have a correspondence, that's very powerful. The point of view from one side of the correspondence sheds light on the other, and the two together are more powerful than just each on their own. The old conventional wisdom used to be that on the Higgs bundle side of the correspondence, that point of view was very useful for seeing some global features of these moduli spaces, in particular, the number of connected components, whereas from the other side of the correspondence, from the representation variety side, that was more effective in understanding properties of individual points in the moduli space, in this case, individual representations. And in particular, it was very powerful in understanding the relation to geometric structures. But what I want to talk about today is really sort of about how this conventional wisdom has broken down and how there's the transfer of information goes more effectively in both directions. So I want to talk in particular about, I want to tell you some things about how the Higgs bundle point of view gives you information about geometric structures. And also, in some sense, how these geometric structures suggest some interesting phenomena in the Higgs bundle moduli spaces. Okay, so the plan roughly is this. I'll start with some background and context for what we're talking about. And then I want to say some things in sort of 3 different settings. The one where we just have a fixed group and talking about geometric structures associated to that. I want to look at sort of the way the picture changes if you embed the Lie group in a bigger group, the real Lie group in a bigger group. So that'll be this G into a G prime. And then look at a situation where you have 2 different Lie groups that are related in some way, and the relations that you see from the different points of view in that sort of setting. Okay, so for some background and context, you probably realize now that many Higgs bundle talks start with SL2R as an example, and it's a very illuminating example. In this setting, so remember, we're talking about objects defined on a surface, which in one sense is just a closed-oriented surface, and the other has a Riemann surface as a complex structure and is a Riemann surface. And we have these 2 moduli spaces that are homeomorphic. In the situation where the group is SL2R, one of the standout features of this is that the moduli space has many components. And so this goes back to Bill Goldman and Nigel Hitchens' descriptions of these from different points of view. The components are labeled by an integer, which is either an Euler number or a Toledo invariant, depending on your point of view. But the thing that I want to highlight for the purpose of this talk is that, among these components, there are some special ones. So these are the components where the integer that's labeling them is maximal. From the two different points of view, you see different things about these special components. On the representation theory side, these components are exactly the ones where all the representations are discrete and faithful. So these are the Fuchsian representations. And out of these, you construct hyperbolic structures on your Riemann surface. So this is a way that you see that these components, these maximal components in this situation, parameterize Teichmüller space for the surface. So there's the relation between representations and geometric structures. From the Higgs bundle perspective, these components, these maximal components in the Higgs bundle setting, have a description, a very explicit description as a vector space. You can identify it with the space of quadratic differentials on the surface. So you get global information about the components from the Higgs bundle picture. If you think of SL2R or PSL2R as contained in the complex group, so you embed this. So this is a situation where we're putting our group inside a bigger group. And now PSL2R is in PSL2C, which you can think of either as the symmetries of hyperbolic space, a three-dimensional hyperbolic space, or as the automorphism group of CP1. So there's relations to geometric structures coming in because of that. And so now the hyperbolic structures become examples of CP1 structures, and these were exactly the structures that Indranil was talking about yesterday. If you think of the inclusion as giving you inclusion of Fuchsian representations into Kleinian representations, which include the quasi-Fuchsian ones, then we're moving from the world where we get uniformization of the compact surface to this situation where we get these quasi-Fuchsian hyperbolic 3 manifolds, which topologically are the surface cross R, but have this nice structure that they have two infinite ends, and at each end you have two Riemann surface structures. This is the setting where the Bayes double uniformization theorem applies. So you get this enlargement of your point of view from the Fuchsian to these quasi-Fuchsian settings from this embedding. So this is, that was particular, a lot of that was particular to SL2R, but there are features of this that are more general, and this is the subject matter of higher Teichmüller theory. So in settings where you replace SL2R by higher rank Lie groups, or real forms of complex simple Lie groups, then in fact, it turns out for most of the real forms, not all, there are some exceptions, but for most of them, the space, the modular space of G Higgs bundles, or by the non-abelian Hodge correspondence, the representation variety, turns out to have special components that have many of the features that the Teichmüller components in SL2R had. So that's why this is called higher Teichmüller theory. You see different things from different points of view. I'm going to just say, two sentences about this, but this is a fascinating subject that could be the topic of a whole workshop and has been. From the representation theory perspective, you can identify these distinguished components in the representation variety, which, like the Teichmüller components for SL2R, have the feature that all the representations in those components are discrete and faithful. There's a different way of identifying the components in terms of the Higgs bundle structure. So we call these the Cayley components. And there, from the Higgs bundle perspective, you can see that the aspect of Teichmüller space, which identified the global structure, generalizes to a sort of a generalization of this, which I won't go into, but is a very pretty picture. So you have these analogs of Teichmüller space in these more general settings, which have these nice features. But so the aspect that I want to focus on in this talk is the relation that you get to geometric structures. So neither of the two aspects that I highlighted there talk specifically about the relation to geometric structures. So what can we say about that? So what do we mean by geometric structures? So the point of view is, the one popularized by Klein. So I looked up, I wanted to see exactly how he formulated it. And if you look on the archive, you'll find a translation of his essay where he actually laid out what the program is. And so this is the way he put it, that as a generalization of geometry arises from this problem, given a manifoldness, so that's a space, and a group of transformations of the same, to develop a theory of invariance, so of that space. So in modern language, geometry is the study of invariance of a space under the action of a group of transformations. And from this perspective, we can identify many interesting geometries. Here's a list, a very incomplete list of spaces and their isometry groups and the corresponding geometries that result from them. But we can go beyond this and talk about geometric structures on manifolds, where by what we mean, so this is in the sense that Indranil was talking about for projective structures, but this applies more generally whenever you have an XG geometry in the Kleinian sense. So if you have a manifold which can be described as covered by open sets with homeomorphisms to the model geometry such that the local descriptions are related by an element of the isometry group, then that puts a XG structure on the manifold. And so you can think of hyperbolic structures in this way, where XG is hyperbolic space. But there are many other examples. And so one of the interesting for us features of having such a geometry is that whenever you have this sort of structure on a manifold, you get a representation of the fundamental group into the isometry of group G, because given any path, any loop on the space, you can cover it with the local patches, and the local descriptions are related by elements of G, so you can concatenate those all together, and for each loop, you get an element of G, and this depends only on the homotopy class of the loop. So the XG structures give you holonomy representations. From this description, you get a holonomy representation of the fundamental group of the manifold itself, but you also, there are interesting representations that arise if you're in a situation where M is related to another manifold. In our case, we're going to be looking at actually bundles over our surface. So manifold M, if you have if you have an M and an S, such that there's a relation between the fundamental groups of these, then you can still look at representations on the target space which come from representations, which come from holonomy representations of XG structures on the big space. And so it'll be in that sense that we'll be talking about geometric structures on manifolds associated with our surface S. And so then we can look at groups where we can look at geometries that are not just of complex dimension 1 or real dimension 2. Okay. In the first situation that was on our list of contents, we want to fix a group G and think about these sorts of issues. So given a group G, so we have our representation variety consisting of representations of the fundamental group into G. You can ask which of those arise as holonomy representations for an XG structure. In the situation, in particular, when the representation variety has multiple components, you could ask if all of the, you can ask in what sense do any of the components parameterize XG structures? And really what we want to talk about is what has this got to do with Higgs bundles? So these questions don't require Higgs bundles to formulate the questions, but we want to see what light is shed on them by the Higgs bundle point of view. Okay, so from the representation variety perspective, a key powerful result is about the representations in the higher Teichmüller components, which are all discrete and faithful, but there's this result which relates them to geometric structures. So the key property turns out to be a property that's called a Nosov. This was defined by Francois Laborie, and I won't go into exactly what it is, but it's a property that certainly the representations in the higher Teichmüller components have. And as a result of this, you can identify a space on which there is a geometric structure defined by the group G. This space comes from it's called a domain of discontinuity in a homogeneous space that is a G mod Q, where Q is some parabolic subgroup, not necessarily the maximal compact. So this is sort of a very general statement, but you identify a domain on which the group G acts properly discontinuously and in fact co-compactly. So this pair, the homogeneous space and the group, defines a geometry in our sense. And the theorem says that for any representation that has this property, it arises as the holonomy of a geometric structure in this sense. So I'll just comment that certainly all the representations in the higher Teichmüller components fit into this framework, but they're not the only ones. Also, these domains of discontinuity, they're very interesting, and they're not unique. You can have different geometric structures associated with the same representations. Also, this says nothing about the structure of these domains of discontinuity or the resulting geometric objects. This theorem doesn't, although there has been recent work which in many cases does identify the topology of these spaces. In particular, shows that they're all bundles over the surface. Okay, so what do we learn from the Higgs bundles perspective? So it's time to say something a little bit more specific about the Higgs bundles we're talking about. Since we're restricting to real forms of complex groups that are subgroups of SLNC, we can describe all the Higgs bundles as SLNC Higgs bundles with some extra features that reflect the fact that we want to talk about a subgroup G. An SLNC Higgs bundle you can also think of as just a Higgs vector bundle. So the objects are rank n Higgs vector bundles with extra constraints reflecting the fact that we're talking about a group G. That gives us, in that setting, we get a moduli space of polystable Higgs bundles, which have many wonderful features that have been discussed in these last 2 weeks. But in particular, for us, what we need to focus on is that the stability property, which allows you to define the moduli space, is equivalent to the existence of a structure on the bundle. So you can think of it as equivalent to the existence of a metric on the bundle satisfying the Higgs bundle equation. This is the curvature of the Chern connection defined by the holomorphic structure on E and the metric, which is the argument of this equation. A metric which satisfies this property allows you to construct a flat connection on E. So the flat connection is constructed out of the Chern connection on that came from the solution to this, and the Higgs field and its dual with respect to the metric. So this is a flat connection on E. Once you have a flat connection, the holonomy of the flat connection defines a representation of the fundamental group into the group G. Using the flat structure, it also allows you to interpret the metric on E as a map on the universal cover of the surface into G mod H. And the equations are equivalent in this setting to saying that the metric viewed in this way is a row equivariant harmonic map in this setting. So this kind of structure is almost enough to define an XG geometry where X is G mod H, but it's not quite sufficient. And here's where the difference comes in. So if you think about what an XG structure on a manifold M is, so the way I introduced it was a collection of coordinate charts, local homeomorphisms in the model space with transitions given by elements of G. So this is local information. But you can repackage the local information into a global map. This is called the developing map. So this data becomes equivalent to a representation of the fundamental group and a row equivariant map on the universal cover that's putting all these local descriptions together. But in order to define a XG structure, you need this global thing to be a local diffeomorphism. So that's the extra bit. You can also think of this developing map. So this is a row equivariant map on the universal cover. The universal cover is a flat bundle, a flat pi1 bundle over the surface. So if you change the fiber of that flat pi1 bundle to be X, then the developing map becomes a section of this flat bundle with fiber X, and the local diffeomorphic condition becomes a transversality condition on the fiber. So what you need then is the data that you get from a Higgs bundle together with some extra conditions reflecting these conditions. So the Higgs bundle technology is very useful for constructing flat bundles with sections. That's sort of the data that comes out of the equations and the stability conditions. But in order to sort of boost that to an XG structure, you need to prove something extra. You need to, which either corresponds to transversality if you're viewing the extra information as a section of this flat bundle, or as local diffeomorphism condition on the developing map. So this is actually this is sort of what goes into Nigel Hitchin's original construction of hyperbolic structures on the surface from SL2R Higgs bundles. And that was sort of really the only example of geometric structures from Higgs bundles for quite a while. But then I think this is really the sort of the breakout point for this perspective, David Baraglia's thesis, where he constructed, used Higgs bundle techniques, from this kind of point of view, to construct RP2 structures out of SL3R Higgs bundles, and also obtained geometric structures from SP4R Higgs bundles. And since then, this point of view has been used very successfully to understand and construct geometric structures in many settings. So there's a very interesting group of young uns who have pioneered this. I've listed some of the names here and some of the settings where these techniques have been used successfully. And I recommend that you Google these names and look up these results. Okay, I just wanted to mention this point that from the Higgs bundle perspective, you can also see, at least in some situations, what happens if the transversality fails. So if the extra condition that you need in order to construct an XG structure doesn't quite apply, is there still something that you can say? And so in the case of SL2R, so there in that situation, we know that the moduli space has multiple components. In the extremal components, the data defines hyperbolic structures. But so what happens in the other components? So with Indranil and Soren Dumitrescu and Sebastian Heller, we looked at this. This similar sort of story was also looked at by Peter Gothen and Pedro Silva. And there you can see that on these other components where the transversality fails, it fails in this nice way that instead of getting a hyperbolic structure, you get a branched hyperbolic structure. So at some points, the identification with hyperbolic space is not a diffeomorphism, but it has this conic structure. These sort of issues are related to this interesting question. In these components where you don't have hyperbolic structures, but you do have branched hyperbolic structures, you can ask, well, is that true for all the representations in the space, or what is the locus of these moduli spaces where the representations come from these branched hyperbolic structures? So in general, this is still an open question, though the conjecture is that you can identify exactly which the representations are, namely the non-discrete ones. Also, learned this week. I should have known before, but Nate pointed me to interesting work that he and his two collaborators have done on similar question for SL2R cross SL2R, which is related to a completely different geometric structure, which I'll talk about later, the anti-de Sitter structure. But there also, when transversality fails, you can see a sort of a branched kind of structure. Okay, so if we look now at what happens if you embed your group in a larger group, so taking as our prototype the embedding of SL2R in SL2C. So I'll just point out that these groups, SL2R and SL2C, are isogynous to these groups, SO12 and SO13. So that's an alternative perspective that is useful. But so now, instead of including SL2R in SL2C, or SO12 in SO13, you can also include these in SL2R cross SL2R, or from the special orthogonal point of view, that's embedding SO12 in SO22 rather than SO13. And that gives you access to a different kind of geometry, because this can be identified as the isometries of three-dimensional anti-de Sitter space. So ADS3, here's a couple of facts about it. You can think of it as the analog of three-dimensional hyperbolic space in the pseudo-Ramanujan setting. You can view both of these spaces sort of in a uniform way if you think of them as being given by a bilinear form on R4. If the signature is 1,3, that gives you hyperbolic space. If the signature is 2,2, that gives you three-dimensional anti-de Sitter space. The three-dimensional anti-de Sitter space can actually also be identified with the underlying manifold of SL2R endowed with its killing metric. So this is an interesting geometry related to representations into these groups, SO22 or SL2R across SL2R. So there's a lot of interesting geometry associated with these, and there's structural sort of theorems. Here's two pieces of information about sort of two different classes of these anti-de Sitter manifolds. There is an interesting class of non-compact ones where under the underlying manifold is the surface cross R. These are called maximal globally hyperbolic spacetimes, and these are very relevant for general relativity. And there's a famous result by George Mess that classifies these by a pair of points in Teichmüller space. So, or really by a pair of Fuchsian representations. So representations of SL2R, both of which are Fuchsian. And that gives you a classification of these. There's a sort of a related but slightly different classification of a class of closed anti-de Sitter manifolds, so compact ones, which up to finite covers are also all quotients of SL2R by a pair of representations, but now one of them is Fuchsian and the other is definitely not, cannot be. So these are descriptions of these manifolds from the point of view of representations. There is a very nice construction of these closed anti-de Sitter manifolds using Higgs bundles. This was one of the items on that list that I had up earlier of situations where Higgs bundles have now successfully been used to construct geometric structures. And Daniele Alessandrini and Chonning Lee showed how to use pairs of SL2R Higgs bundles. So the ones related to these pairs of representations to construct these closed anti-de Sitter manifolds. And one of the nice things that you get from this construction is you get some global information about the structure of these manifolds. they get explicit topological and geometric information about them from the Higgs bundle construction. Okay, so in the last part of the talk, I want to say some things about what you see if you compare two different situations. So if you have two different groups, just in general G1 and G2, one setting where this is a very important consideration is in the setting of three manifolds. So there, by Thurston's geometrization conjectures or theorem, you can break up your three manifold into pieces, each of which has a geometric structure in our sense. There's a list of 8 geometries that are possible. But so in that setting, it becomes, the question comes up, what are the transitions between these sorts of geometries? You can imagine that you might be interested in how you might move from one kind of geometric structure to another. There's a sort of related transition that was described by Jeff Danziger, looking at the geometries associated precisely to SL2R cross SL2R or SL2C. So this is the one that I mentioned earlier. And so this corresponds to transition between three-dimensional hyperbolic geometry and three-dimensional anti-de Sitter geometry. So the way Jeff Danziger described these geometries and the transition between them was in this way. So, these are both described by a bilinear form with different signature. He constructed this family of bilinear forms where the parameter S controls one of the signs. So in this setting, you get a family of structures which depend on the sign of S and give you a transition from hyperbolic space to anti-de Sitter. He analyzed the geometry of the singular fiber and called that a half-pipe geometry. So this is the setting from purely geometric perspective. Sort of motivated by this, that's me and Laura Shaposnik, sort of thought, well, we wonder if there's any sort of analogous transitions that you might see purely from the Higgs bundle perspective. What we're looking for is, given two moduli spaces of Higgs bundles corresponding to the two different groups, and in particular, we're talking about these two groups. If you want to look for sort of a transition, you want a common, convenient common setting where both of these are located so you can locate the transition. And then really our sort of vague quest is to find interesting paths between these. So this is suitably vague, and there's still not all that much we can say, but I think there are sort of interesting things to look for here. The setting where we can look for the Higgs bundle version of this transition is where okay, never mind. So both of these groups are real forms of SO4C. So that's an obvious setting. It's from the Higgs bundle perspective, it's sometimes more convenient to look at the double covers of these groups. Here it's SL2R cross SL2R. The double cover of this is SL2C cross SL2C. And the SL2C that is the double cover of this sits inside here as a real form. So this is actually can be viewed as a real form of this complex group. It's the real form related to this anti-holomorphic involution. So this is the setting where we can talk about Higgs bundles related to the two groups and maybe see how you can transition from one to the other. What can you see? So this is what we're looking for. Interesting paths in these two Higgs bundle moduli spaces, one associated to SL2 SL2R cross SL2R, and the other associated to SL2C. And somehow, you know, paths where these are degenerating to a common point where a transition is taking place. But I mean, we want these paths to be within each of the moduli spaces. I mean, the moduli space, the big moduli space is a connected space. So, you know, you can construct a path from any point to any other point. That's not so interesting. They've got to be somehow constrained. What can you say? So what do the Higgs bundles look like? I mean, you know, the power of Higgs bundles comes from the fact that you have very explicit information about what the objects look like and a lot of extra structure. So what do we have in this situation? Well, so an SL2C Higgs bundle is just a rank 2 Higgs bundle. So it's a rank 2 holomorphic vector bundle and a Higgs field in the usual way. The SL2R Higgs bundles viewed as SL2Cs with extra constraints are rank 2 bundles of this form, a line bundle plus its dual, and the Higgs field has to have this particular structure. So the object is determined just by a line bundle and these two pieces of the Higgs field. So instead of writing it out like that, I'll just record the 3 pieces of information. So a triple like this corresponds to an SL2R Higgs bundle viewed as an SL2C with special features. In our space, our product of SL2C cross SL2C, so now the objects are a pair of objects like that. The ones that correspond to the real form SL2C sitting inside there are the pairs where the two Higgs bundles differ just by the minus sign in the Higgs field. So you have an E phi and an E minus phi, a pair like that. The SL2R cross SL2Rs correspond to a pair, each one of which is of this form. So that's why I've just recorded the information in that way. If you want to think of these as sitting inside the bigger space SL4C, then this is the way they look. But in fact, I don't think we really need to bother with that. That's why I put it in a lighter color. Let's see, did I? Okay, so what can we say about paths within these spaces? I mean, I'm not sure that this is definitely not the only way you could think about constructing paths, but here's one interesting way that you can do it using you know, key features of the Higgs bundle moduli space, namely the fact that it has a C star action, which has come up in several talks in this meeting. We can look for the place where these moduli spaces meet, namely in the nilpotent cone of the moduli space. So that's the locus where the Higgs field is nilpotent. That has a very special role in many different ways in the Higgs bundle world. But for us, it's sort of going to be the locus where these two different real forms could, in principle, come together. So on the SL2R side, where we have Higgs bundles determined by a line bundle and two pieces of the Higgs field, you can look at, so this is called the upward flow. I still don't know why the parameter going to 0 is upward, but that's, so if you look at the C star orbits acting on SL2R Higgs bundles, then what that does is it scales the piece in the upper right-hand corner to 0. So taking the flow, taking the limit as lambda goes to 0 sends you to a fixed point for the C star action. The C star fixed points are very well, I mean, we can identify what they are. In the SL2R case, in the SL2C case, the fixed points are all have this form. They're exactly the SL2R Higgs bundles where one of the pieces in the Higgs field is 0. And the flow, taking the upward flow, scales that upper piece to 0. That's exactly what it does. On the other side the other side meaning the other kind of object that we want to look at, corresponding to the SL2C Higgs bundles, we can again take the upward flow, and this will flow these SL2C Higgs bundles to a fixed point in the nilpotent cone. The difference between the two that occur in a pair corresponding to an SL2C goes away when you take the limit as lambda goes to 0. So both of these flow to the same SL2C fixed point. We also will need a flow between fixed points in the nilpotent cone. We'll see in a minute why those come up. And so those correspond, I guess, to downward flow. That corresponds to taking a flow along a C star orbit, letting lambda go to infinity, or 1 over lambda go to 0. That remains, that's a flow entirely within the nilpotent cone, but can take you from one fixed point to the other. Okay, so in the last couple of minutes, here are two specific kind of paths of this sort with maybe geometric interest. So this corresponds to the situation where the geometries correspond to, on the one side, the SL2R cross SL2R, these correspond to the non-compact anti-de Sitter manifolds classified by Mess by a pair of Fuchsian representations. So if we start with a pair of Higgs bundles in the component corresponding to the Fuchsian representations, that's the Hitchin component, the maximal component in the SL2Rs. So there, the component of the Higgs field that is not allowed to vanish is identified as a 1. And we have the other part is parameterized by a quadratic differential. So we have a pair of those. We can take the C star flow in the limit as lambda goes to 0. So that eliminates the Q's. So both of these end up at the same fixed point. If we start, so that's what you get on the one side. On the other side, we have a pair of Higgs bundles, an E and a plus or minus a Higgs field corresponding to something coming from SL2C. But if we knew that that corresponded to a quasi-Fuchsian representation, then we would be in a situation where the geometric structure associated to that corresponded to a quasi-Fuchsian hyperbolic 3-manifold. So at least we'd sort of be in the right sort of setting. And so by this nice result of Alessandrini and Lee, we know that if we take our SL2C Higgs bundle of this form, so it's not exactly, so it's not at a fixed point, but the way it differs from the fixed points accessed by this one is that the bundle is not k to the minus a half plus k to the half. It's a non-trivial extension of that. But the Higgs field is the same. So these give you quasi-Fuchsian representations, and these we can flow to this double point by taking the downward flow, because the downward flow here scales the extension class to 0. So here we have a path within the Higgs bundle case that sort of is going between these two geometries. If we want to find a path that relates to the compact anti-de Sitter manifolds that were constructed by Alessandrini and Lee, then you have to start with two different SL2R Higgs bundles, one of which is in the Hitchin component and the other of which is not. So the degree of L is less than G minus 1. Now when you take the flow as lambda goes to 0, these go to different fixed points. So we end up with two different fixed points. We could take an SL2C pair. In fact, any pair will flow to some fixed point. So you can, but we know that both of these go to the same fixed point. So you can get a path going to either one of these. So now these paths don't join up. So you need a path that interpolates between the two fixed points. So that's, I mean, there are restrictions on when you can do that. They're not any two C-star fixed points are joined by a flow line like this. But you can analyze when that can happen. So this is nicely described in a paper of Graham Wilkins. You see the relation by understanding these in terms of Hecker transforms from the one to the other. And the condition for this non-maximal flow fixed point to be joined to the maximal one by a C-star flow line is that basically it should be related by Hecker transform. So the L should be related to the square root of the canonical bundle by a divisor. And the Higgs fields, the piece there, the parts that don't vanish and determine the fixed point, so that's the 1 over there and the beta over there, should be related in this situation by the tautological section determined by the divisor. So if you make your choices so that these conditions are satisfied, then you do have a flow line from there to there. So that would join up the path that we constructed here and the path that we constructed there. The only sort of fly in the ointment here is that this path is, I mean, it's somewhat special, but it's not in either of the spaces corresponding to the geometries that we were targeting. So I don't know what it means, but at least it's a pretty path. Okay.
Is this on? Oh, yes. Are there more questions?
Hi, thanks. So I was curious, does half-pipe geometry also appear somewhere in this Higgs bundles picture in the transitions?
Yeah, I mean, excellent question. Hopefully, I mean, the isometry group for that is SO12 cross R. So that at least tells you what kind of Higgs bundles to look for, but we haven't, and I think it's quite likely that you can actually give a description line and see exactly how it happens, but we haven't figured that out yet.
Do you have a harmonic map interpretation to the different symmetric spaces involved here of this transition that in the example, in the case that you are studying?
No, but that's obviously a good question. I mean, the Higgs bundles certainly we know have harmonic map. I mean, there are harmonic maps associated with those, but you want to see how the transition happens in terms of the harmonic maps. Yeah, no.
Yes.
Excellent question.
Yeah, just a short question is, do you have any idea about relationships between these transitions and some kind of physics stuff? Like if you're doing anti-de Sitter space or something like that?
No, I'm the wrong person to ask whether, I don't know. I mean, has there been any physics perspective on the geometrization of three manifolds? Is it? Yeah, I don't know. I mean, these globally, maximal globally hyperbolic, I forget the words, but the non-compact hyperbolic anti-de Sitter manifolds, these are the ones that are relevant for general relativity. They have the structure that you need in order to make sense of them as space-times. Sorry? Sure, oh, please. Quasi-Fuchsian what? Oh, so he did? Oh, so, oh, please, please send me that. Oh, so that's answering your question then. But he was this from a Higgs bundle perspective? No. Right, I mean, the half-pipe thing is singular, so so was that sort of a different perspective on Jeff Danziger's result, or? Forming the quotients. Anyway, we can talk about it, yeah.
Maybe just add to that, I don't know if the context of that paper, but one place where ADS spaces arise in physics is this thing called the ADS-CFT correspondence to understand gravity. Right. So I don't know if that was the context, but there's a, yeah, okay. Which is like holography. So you try to understand gravity in the ADS space or asymptotically ADS space in terms of some theory that lives on the boundary. But I guess your spaces are compact, or I'm not sure, but anyway, maybe there's a connection there.
Any more questions? Okay, well, if not, let's thank Steve again.